Hi, let us introduce QuickSort algorithm. QuickSort is a divide and conquer algorithm, which means it first divides your input array or list in two parts, then it sorts those two parts independently. It's similar to merge sort in that way because merge sort is also divide and conquer. The difference here is in merge sort, the merge process is complex, the division is simply half of division, but in quicksort, the partition process or the division process is complex. We call a function called partition that divides your list into two parts, and these two parts need not to be of half of size. In merge sort, they are of half of size. The partition function ensures that you have some elements in one half and some other elements in the other half, and then this sorts these two parts independently. That's how quicksort works. So in merge sort, merge function is complex. In quicksort, the partition function is complex. That's the key function. Partition function is the key function in quicksort, like merge function is the key function in merge sort. But they both are divide and conquer. The next point is worst case time complexity of quicksort is big O of n square. If you compare it with merge sort has big O of n log n time even in the worst case, but it is big O of n square. But despite having big O of n square worst case time, this is considered faster than merge sort. The reasons are it is an in-place algorithm. See, this is arguable. Saying in place is arguable because it requires auxiliary space for the recursion call stack. But when we say in place, we mean here is it does not create auxiliary arrays to partition the array. It does not copy or input data to some auxiliary array. It only uses auxiliary space for recursion call stack. So the partition function of quicksort, if it uses Longmuto or Hover's partitions, these partition algorithms partition the array in place. They do not need an extra array. So partition is in place. The only extra space you require is only for recursive calls. Since it is an in-place algorithm, it's working on the same array or list, it is cache friendly as well because you are more likely to have all the items in cache, and that's the reason it is considered faster than merge sort, because merge sort, it creates auxiliary arrays to sort. Average case of quicksort is big O of n log n. Although the worst case is big O of n square, on average it works in big O of n log n time. It's a tail recursive algorithm. See, what is a tail recursive algorithm? If a recursive function does recursive call as the last thing, then this recursive function is called tail recursive. And such functions can be rewritten in such a way that you can remove the recursive call and you can write it as a loop. So in merge sort, if you remember the merge sort, the last thing that was happening was merge function, not the recursive call. In quicksort, when we study quicksort, we'll see that the last thing that happens in quicksort is a recursive call. So one recursive call can simply be replaced by a loop in Python or go-to statement with Java and C++. So we can replace that one recursive call in quicksort, and many compilers do this optimization automatically. But Python does not do tail call optimization or tail call elimination. We have to do it as a programmer if we are writing the Python tail recursive code. As we've discussed earlier, partition is the key function in quicksort, and we are going to discuss three different approaches for partition. We are first going to talk about naive partition, which is going to be inefficient, but the good thing about naive partition is it is stable. So quicksort is not stable if you use these efficient partition algorithms, but if you want a stable version of quicksort, you can use naive partitioning. These two algorithms are in place, they are faster, they just do one traversal of the array or list and do the partition, but naive requires three traversals, but it is stable. But in general, if we are using that much work, then quicksort is definitely not as efficient as it is generally talked about, right? So naive partition is generally not used, and that's why the Longmuto and Hover's partitions are preferred, and among these two, Hover's is the most efficient, right? Hover's is the most efficient partition scheme. That's what is used in practice, and with Hover's partition you get a fast sorting algorithm, but which is not stable. So many library implementations, they use quicksort when stability is not required. For example, in C++, there are two functions, sort and stable sort. The sort function uses quicksort variation internally. It uses an algorithm called intro sort, which is a hybrid of QuickSort, heap sort, and insertion sort, but mainly QuickSort based. C library has a function called QSort, right? And QSort, as the name suggests, is a QuickSort implementation. Java uses QuickSort for primitive data type sorting, right? For primitive types, it uses QuickSort dual pivot QuickSort algorithm, a variation of QuickSort for sorting purpose. For non-primitive data types, Java uses timsort algorithm, which is also used in Python. And timsort is a variation of merge sort. So Python and Java's non-primitive type sorting, they are based on merge sort. They are stable. But other algorithms like C++ sort, C QSort function, Java primitive type, they use QuickSort algorithm variation for sorting purpose. If we compare QuickSort with merge sort, see, when you don't need stability, then QuickSort is definitely the fastest algorithm. QuickSort or its variations, the intro sort version, they are the fastest variations which are actually used in libraries also. But if you need stability also, then merge sort is preferred.